Okay. So there are two very efficient techniques we use to graph linear equations. One of them is the X and Y intercepts. Now, remember, the X-intercept, guys, is where a graph intersects the Y-axis, the X-axis, and the Y-intercept is where the graph intersects the Y-axis. Now, what you have to remember is this: 2 points determine a line. So having said that, guys, when you're graphing on MyMathLab, you need to have at least 2 points in order to be able to sketch a graph in MyMathLab. And when I go in through the assignments, I will do some demos for you so you guys can actually see it. 2 points determine a line. So the other method we use to graph linear equations very effectively is the slope-intercept form. And I will be going over both of these in a minute with some examples, okay? Now, the slope-intercept form, AKA y equal mx plus b, guys. By the way, y becomes f of x. So if we were to rewrite this in function notation, it would be f of x equals to mx plus b. This is the same thing as y. So y and f of x are exactly the same thing, guys. So if you should see f of x, just know that is simply y. So f of x is y, and y is f of x. Any questions, guys? All right, so now let me go ahead and present you with some examples, okay? So first, we're gonna talk about the X and Y intercepts. Now, in order to find the X-intercept, if you're looking for the X-intercept, what you do is you plug in 0 for Y, so let Y equals to 0, and then solve for X. Likewise, if you're looking for the Y-intercept, you want to let X equal to 0 and then solve for Y. Now, remember, 2 points determine a line. So once you have your X-intercept, your Y-intercept, you essentially have your 2 points and you're pretty much ready to go ahead and graph, guys. So here's an example of an equation where we're going to graph it using the X and the Y-intercept, guys. Now, for this one right here, it is negative 4x plus 2y is equal to negative 4. Now, for this particular problem, let me adjust my volume a little bit here, guys. Hold on a moment. All right. I'm trying to avoid that echo, but that echo is there. Let's see if this helps. Okay. I'm still hearing that echo. Okay. Hold on, guys. No. That's not helping. Okay, how about now? Is that better? No echo? Yeah, that sounds better. Can you guys hear me?
Yes.
All right, perfect. All right, guys. So let's go ahead and find the X and the Y-intercept for this one. So first, we're going to start with the X-intercept. Now, when you're finding the X-intercept, you just go to the equation, substitute 0 in for Y, and then you want to go ahead and work this out to solve for X. So essentially, 2 times 0 just cancels out, leaving you with negative 4x is equal to 4. So you want to divide both sides by negative 4, everybody. So x will equal to negative 1. So that's your X-intercept, negative 1, 0. By the way, guys, whenever we talk about the X-intercept, it represents a coordinate point on the X-axis.
Wouldn't it be 1?
Point on the X-axis has a 0 component for the Y and some other value component for the X. Now, let's move on to the Y-intercept. To find the Y-intercept, we're going to go into the equation, substitute 0 in for X.
Can I stop you for a second?
Yes, absolutely.
Wouldn't it be 1 because isn't it equal to -4?
Oh, I left out my negative. That's why. You're right. Let me put the negative back in here. Okay, so then that's gonna wipe this out and wipe this one out. So yes, that's a positive 1. You're absolutely right. Now, guys, over here, if we're going to find, let me use a different color here. We're going to now find the y-intercept. Let me make sure I put the negative this time, okay? We substitute 0 in for x to solve for y. So essentially, this cancels out, leaving you with 2y equals to a -4. You divide both sides by 2, so y will equal out to -2. So your y coordinate point would be 0, -2. And just like with the x-intercept, guys, the y-intercept is a point on the y-axis. So the x component is 0, and there's a y component, okay? So now that you have these 2 points, you are ready to graph this equation because 2 points determine a line. So you go to the xy plane, and let me do a quick sketch right here. I am going to go to the xy plane, guys. Remember, for this one right here, the x-intercept is 1, 0, while the y-intercept is 0, -2. So this is your y, and this is your x-intercept right here. So you just go to the xy plane, find out where your x-intercept is at 1, 0. Find your y-intercept, which is located at 0, -2. Plot your point. So now that you have your 2 points, you're ready to sketch your graph. So all you have to do now is just go ahead and draw the line, guys. There's your line for that equation. -4x plus 2y equals to -4. And that's it, okay? So using the x and the y-intercept to graph, guys, very efficient. So let me do a secondary example, and then I'll move on to the other method with you all. So for the second example, this time, guys, it is 4x minus 5y minus 20 equals to 0. One of the first things I like to recommend to students about this type of problem right here is to rewrite it in this form. By the way, this form is called standard form. Don't put too much emphasis on the form, guys. And pretty much it is ax plus by equals to c. Normally, when we work with the linear equations, either they're in slope-intercept form or point-slope form, they rarely ask you to put these in standard form, but you should be aware of standard form. And standard form simply means you have your variables on one side, and on the other side, you have your constant. Every once in a while, they'll give you standard form just like the problem is written too. But for the majority of the time, you have your constant right here on the right side. So we're going to move that -20 on the right side. So this equation becomes 4x minus 5y equals to 20. Now, guys, be careful with my math lab. If my math lab says to use x, y-intercept to graph, you must use that. Even if you get the correct graph, if you don't use the x and y-intercept, the computer will mark the problem wrong. So be careful. So now the equation is in standard form. So now we're going to go ahead and find the x and the y-intercept. So let's do it, guys. For the x-intercept, remember, we're going to plug in 0 for y and solve for x. Okay, we're going to plug in 0 for y and solve for x. Now, if we plug in 0 for y, guys, that's like saying this term right here doesn't exist. So what do you have left over? 4x equals to 20. 4 times what gives you 20? This is an equation. Okay, so if you're solving for x, you would divide both sides by 4, or just ask the question, 4 times what gives you 20? That would be 5. So for this particular problem, guys, once you know you're going to have to solve for, you're going to have to solve for the x-intercept, you just plug in 0 for y. That's like saying the term is not even there. If I was in the classroom with you, I would call it the cover-up method, but since I'm not here, it's easier to say, oh, let's pretend the 5y term is not even there. Likewise, if you're looking for the y-intercept this time, you're going to substitute 0 in for x to solve for y. So this is like saying, oh, 4x is not even there. So what do we have left over? -5y equals to 20. Solve this equation. divide the 20 by -5 to get your answer. Or -5 times what number gives you 20? That would be a -4. So guys, this is what's happening with these problems. Essentially, you plug in 0 for one variable and solve for the other one. When you plug in that 0, the term cancels out. So this one turns out to be a -4, okay? So there's your 2 points. Here's the first one. Here's the second one. And so now you want to go to the XY plane, find your Y-intercept along the Y-axis, plot your point. Find your X-intercept along the X-axis, plot your point. And just like that, guys, 2 points determine a line. There's your line, and you're done. That's it. By the way, you will see some of these same questions in the video for lesson 2.1 and 2.2, actually 2.3 and 2.4. All right, guys. So now let's go to the second method. The second method is the slope-intercept method. Now for the slope-intercept method, okay, let me give you some background info. First and foremost, you have to rewrite your equation in y = mx plus b form, as in solve for y, as in isolate the y variable. So it needs to be in this form, guys. Now, remember, this can also be written in function notation as f of x equals to mx plus b. All right? Now, we just finished talking about finding the x and the y-intercept. This intercept right here is referring to the y-intercept. The y-intercept is a coordinate point, 0, comma, some y value. Now think about it, guys. Let's go into the equation. If we're finding the y-intercept, okay, we're going to plug in 0 for x. That's like saying this term doesn't exist. So what do you have left over? Y is equal to b. So your y-intercept is whatever that b value is. Whatever it is, that's your y-intercept, everybody. Okay? Now, the m represents your slope. The slope is defined as a vertical change over a horizontal change. A vertical change over a horizontal change, guys. So some of you commonly refer to it as the rise over the run. So this is what students commonly use it as, the rise over the run. I wrote the wrong thing, the rise over run, guys. So when you're graphing using slope-intercept form, you first want to go ahead and plot your y-intercept, and then you're going to use the slope to plot a second point. But guys, as always, you have to make sure the equation is in the form of y = mx plus b first. If it's not in that form, it's going to be really difficult to graph it, okay? Now, here's an example problem, guys. F of x, let me use a different color here. F of x is equal to, let me see here. Let's find an easy one. Hold on a sec. That one looks too hard. Okay, let's do this one right here. -2/3 x plus 1. All right, guys. Now, this is in function notation. If you're not comfortable with function notation yet, you can always replace f of x with y. Remember, they're interchangeable. F of x is y, y is f of x. So if you're not comfortable with function notation, revert back to using y, guys. So we can rewrite this as -2/3 x plus 1. Now, we're going to identify the y-intercept. The y-intercept for this one is going to be 0, 1. Why is it 0, 1? Right here, guys. Remember, this value right here represents the b value or the y-intercept. Or you could say, if I plug in 0 for x, what's going to happen with the -2/3 x? It's going to cancel out because you're substituting in 0 for x. So there's your y-intercept. Now, your slope. The slope for this one is the coefficient of x, and the coefficient of x is -2/3. Now, be careful when you're graphing with a negative slope. Because it's a negative, guys, okay? Be very careful. The negative says to travel down 2 units, okay, because it's negative. And then the denominator here represents your run, so you want to go ahead and move to the right 3 units and then plot your second point. Now, once again, from your y-intercept, you travel down 2 units, move to the right 3 units, and plot your second point in order to be able to graph this linear equation. So guys, I'm going to go ahead and go through the process of graphing. Remember, you will see these questions in my math lab. Now, when you see these questions, guys, they will tell you specifically which method to use. Are you going to use the Y-intercept, or are you going to use the slope-intercept form? So be careful, read the directions, because even if you get the problem right and you use the wrong method, the computer will not give you credit for the problem. So be careful, guys. All right, so here's the first thing we're going to do. Plot the Y-intercept. The Y-intercept is at 0, 1. There it is. Now your slope is -2/1. So from positive 1, the Y-intercept, guys, we're going to travel 2 units down. So that's 1, that's 2 units. And then we're going to travel 3 units to the right. So that's 1, 2, 3 units to the right. And there you go. Just like that, you have your second point. Now, let's say you're graphing on an XY plane that was limited. You didn't have enough space to travel down. If you did not have enough space to travel down, you could do it in reverse. You could go up 1, 2 units and move to the left, making up for that -3 units. So 1, 2, 3 units. And it still takes you on the same trajectory, guys. So remember, 2 points determine a line. Once you have those 2 points, you're ready to go ahead and sketch your graph. And that's the slope-intercept form, guys. Ask me some questions. You guys are not asking any questions.
Hold on. Where's the third dot coming from on the top left?
Okay, I created another point and I used the slope, okay? So let's say I didn't have enough room to go down 2 units and move to the right 3 units. I could do it in reverse. I could do this instead, +2 over -3. So I would go up 2, which takes me here, okay? 1, 2 units, and then move to the left. By moving to the left, that's making up for the negative, okay? So moving up is positive, moving to the left is negative, so I still have a negative slope. And what you should notice is that that point is still on the same line, it's still on the same trajectory, okay? So we're just creating more points on the same graph. Math is all about flexibility and versatility. There are other ways to do these problems, guys. You don't necessarily have to do them just one way. Oh, negative slope, down 2 over 3. It doesn't always have to be like that. You could do it in reverse. Up 2, left 3. It's still a negative slope. Okay, you sound like you had another question. Go ahead and ask me.
No, I was just saying, so just basically just flip it to make another point. Like.
Yes, absolutely.
Okay.
Mm-hmm.
So if you had a positive fraction, like 2/3,
right,
then you can go -2 over -3 also.
And we're gonna do another one, okay? But absolutely, Jennifer, a -2 over -3 would still maintain that positive value. Absolutely. It's all about flexibility, guys. All about flexibility. So guys, here's another one. -2x plus 3y is equal to 6. Now, on this one right here, you will notice it's actually given to you in standard form. This particular problem right here, it would be best if you were to graph it using Y-intercept, but the problem wants you to use slope-intercept. So if they want you to use slope-intercept, you have to use slope-intercept. So on this one right here, guys, the first thing you have to do is to go ahead and solve for y, so you can rewrite the equation in y = mx plus b form. And to accomplish this, you want to take the -2x, guys. It's negative on the left side. You're going to move it over to the right side. And so because you're moving it to the right side, it's going to become a positive. Now, you want to divide every single term by 3. Every term, because remember, we're trying to solve for y. We're isolating the y term. Now, the equation is in y = mx plus b form. So once you have it in that form, you can definitely eyeball this and say, oh, my y-intercept is 0, 2. Remember, guys, when you're doing this, you are simply getting rid of that. Okay?
Are there leftovers?
Is there what? Oh, I don't think that one was directed at me. Okay. So guys, for the y-intercept, you plug in 0 for x, solve for y. That's all we're doing. So by plugging in at 0, basically this term completely cancels out. All right. Now for the slope, everybody, the slope is 2 over 3. And this time it's a positive. So you're going to go up 2 units and then move to the right 3 units and plot your second point. So we're going to go ahead and go to the XY plane so we can sketch the graph of this. Be careful when you're graphing on My Math Lab. You need 2 points to graph, 2 points to determine a line. And you will see that throughout the remainder of the semester, guys. 2 points to determine a line, you must have 2 points. There's only one problem where you don't have to have 3 points, and that's in chapter 3, but that's way later on, guys. So here we go. 0, 2, guys. Positive 2 is located right here. And then they want you to go up 2 and move to the right 3 units. Bam. Now, like Jennifer was saying earlier, what if it was a positive slope? Could we do it in reverse, as in do down 2, 1, 2, that's a negative, and move to the left 1, 2, 3? Could we do that as well? Absolutely. We still have a positive slope, because if you go down, that's negative 2 units. If you move to the left, that's another negative. So a negative divided by a negative is still a positive. And again, you can check yourself, guys. How do you check yourself? Notice the points are on the same trajectory. They are in the same line. So there's your graph, people. And just like that, we're done. Graphing, I don't know why, but students have a major problem, big problems with graphing. I don't know why, but whatever, guys. So graphing is not as hard as you guys may think. Worst case scenario, if you get stuck, you can always use on a T-table or a T-chart. Just go back to this, to the basics, guys. You know, plug in some values for X and then solve for Y. And then once you find the points, plot them on the XY plane. It doesn't have to be complicated. You just have to know if you get stuck, just plug in some values for X, solve for Y. That's all this is about, guys, okay? Now, there are some special cases that we encounter while graphing. Here's one of those special cases, guys. 3y minus 9 equals to 0. A problem like this, they ask you to go ahead and graph it. First thing you notice, oh my goodness, there's no x. There's no x variable. So the minute you notice there's no x variable, it means that when you graph this, the graph cannot intersect the x-axis. So you have to draw the graph so that it's running parallel to the x-axis. So which means it's going to be a horizontal line. Now, once you know this, you need to go ahead and go over here and solve for y. We're going to solve for y. In other words, we're going to rewrite this in slope-intercept form, y equal mx plus b form. So I'm dividing both sides by 3. So this leaves me with, my pen is not writing over here, guys. Okay, there we go. So we get y equals to positive 3. This is what you're going to graph, guys. Y equals to 3. Now remember, you need 2 points to graph. So if you're graphing y equals to 3, you want to go to the xy plane, find where y is equal to 3 at your first point. You need a second point. So to get to that second point, you pretty much go along the horizontal and plot a second point anywhere on that horizontal line, okay? And the computer will generate the graph for you. So anywhere, guys, make sure the line is horizontal, plot a secondary point, and the computer will generate the graph for you. Any questions on this one? Okay, I like to call these the ambiguous graphs because they're missing a variable. So here's another one, guys, where you're going to be missing a variable. This time it is 3x minus 12 is equal to 0. Now for this one, we're going to start off by adding 12 to both sides, which reminds me, I did not mention the fact that there's no y variable, there's no y. So then when you sketch the graph of this one, the graph has no business intersecting the x-axis. So this graph has to be drawn in a way so that it never intersects the y-axis. In other words, it has to run parallel to the y-axis. So when you sketch the graph of it, guys, you go to the xy plane. Okay, you find where x is equal to 4. Plot your point here. Let me use a different color. Plot your point at x equals to 4. Okay, remember it has to run parallel to the y-axis, so it never intersects the y-axis. So we're going to go ahead and go anywhere along the vertical line and plot a secondary point, it really doesn't matter, guys, wherever, okay? Remember, this is your y-axis right here, and this is your x-axis. So guys, be careful. Since the equation contains x, it can only intersect the x-axis. The previous one was y equals to 3, because only one contains the y, it can only intersect the y-axis. By the way, I forgot to mention this, but this is in one of the previous videos. We also talk about slope, just like we did with the previous 2 examples. We saw a positive slope and negative slope, but there's 2 other types of slope, guys. For the vertical line reflects an undefined slope. Undefined slope when you have a vertical line, undefined slope. However, if it's a horizontal line, like the one we graphed previously, this one represents 0 slope. Okay, now I could elaborate on this a little bit more, but it's in the video. I will let you guys watch it because I go thoroughly into the difference between undefined slope and 0 slope and how you can tell the difference between the two. So make sure you guys watch that video on lesson 2.3 and 2.4. Okay.
So for answers, will you have to choose like undefined slope for a vertical line or 0 slope for a horizontal line?
Yes, there are some problems like that in lesson 2, 3, 2, 4. Yeah, they will ask you to find the slope, and then you have to determine what type of slope is it. Is it positive slope? Is it negative slope? And is it 0 slope or undefined slope? Yep. On the test, you may get a question similar to one of the previous problems we did. I think the one we did was negative 2x plus 3y is equal to 6. They will give you an equation like this, and they will ask you to find the slope and y-intercept. So you would just go ahead and solve it for y, write it in y equal mx plus b form. And so you should be able to identify your slope and y-intercept. But every once in a while, they'll just give you an equation, y equals to 3. And they will ask you, what's the y-intercept? Well, obviously y is equal to 3, so your y-intercept is 0, 3. But then when they ask you for the slope, okay, you have to remember, this is a horizontal line. There's no rise in this problem, it's just running. So therefore the slope must be 0, okay? So yes, you have to be aware of those. But like I said, I talked about this in the video, so make sure you guys go back and watch the video. And the beautiful thing about all this technology, guys, is that you can go ahead and skip through the video, find the section that you need, and just watch that and just move on. So you don't have to linger through the entire video. And you can even speed up the video. I love that part, okay? So guys, now I am going into lesson 2.5. Let me check time. Oh my goodness, look at the time. Okay, so I am going to do these quickly because, guys, I'm going to tell you right now, you will not see these on the test, okay? But you need to know transformations. This is where we take functions and move them all over the XY plane using different types of transformations, okay? So I'm going to highlight some of these transformations. Additionally, guys, these are calculator problems. You can type them into your graphing calculator. You must have a graphing calculator in order for this to work, okay? Graphing calculator. Now, as I go through this, guys, you will see some of these problems on the assignment. What you have to be able to do is to identify the transformation and then use the transformations to be able to identify the correct graph for the function. That's all you're doing with this part. But no, you're not going to see these on the test, okay? You will see them on the assignment. So guys, I am going to look at specifically 4 transformations with you. First, we're going to look at the vertical shifting. Now, the vertical shifting is just like what it sounds. It either moves the graph up or down in the same direction, And like I said, I am making this as easy as possible. And so, I forgot to mention something else. I'm making this as easy as possible, guys, so I'm gonna quickly go through it. What I forgot to mention is this, the functions we are going to look at in order to perform the transformations. We are going to look at primarily 3 functions, okay? So here's the first one we are looking at, guys, and that is the quadratic function. And for the quadratic function, guys, when you graph it, the graph looks like the letter U. It resembles the letter U. Now, the domain of this graph, guys, is all x's from -infinity to +infinity. The domain is the x's, while the range represents your y value. Now, the range, the y value for this one starts at 0 with a bracket, guys, and in the graph continues all the way up to +infinity. By the way, this particular graph is an even function, which means if you were to go ahead and draw a line straight through the middle, the left side, here, let me use a different color. The left side of the graph would mirror the right side of the graph and vice versa. That is called symmetry. We call that y-axis symmetry. And that's also in the first video, guys. So that's the first one we're going to look at. When we look at the function equation, it is in the form of f of x equals to x squared. So here's what I want you to know about this, guys. This is a quadratic function. This is what the function equation is. And this is what the graph looks like, because we're going to be moving the graphs about. So this is all about looking at the graphs, okay? You have to be able to recognize the graphs. Here's the second one. The second one is called the absolute value. Absolute value. And for the absolute value function, the equation is f of x equals the absolute value of x. When you sketch the graph of it, guys, when you sketch the graph, okay, the graph will look like a letter V. Here, let me use a different color so I can sketch it out for you. It will look like the letter V, okay? Now, the vertex is very sharp, so be careful with that. Now, just like with the quadratic, the domain of this function is going to be all reals, every x, guys, positive, negative, it's all reals. However, the range, which we refer to the y values, is from here up to +infinity. So the range for this one will go from 0 up to +infinity. Now, once again, guys, what are we looking for? We are checking what the equation or the function looks like, and then what the graph of the function looks like, because that's what we're going to use for the transformations. Now, one more thing. This graph is also even, as in, once again, if you draw a line straight through the middle, the left side looks exactly like the right side, or the right side looks exactly like the left side. We call that balance or symmetry, guys. Now, by the way, I talk about even, odd functions in a previous video too, so make sure you guys watch it, okay? Now, here's the third function, guys. F of x is equal to the square root of x. We call this a square root function. Square root function. Now, for the square root function, when you graph it, the graph is exclusively in the first quadrant, guys. That's the square root function. Now, the description we give this one, you know, the quadratic looks like a U, the absolute value looks like a V. And this one, I don't know what you guys are seeing. A lot of people are seeing a square root or the Nike logo. So it's up to you, whatever you want to use. It really doesn't matter. But guys, what I want you to notice is that since the graph is exclusively in the first quadrant, this means that the domain for this particular function, the x's of this function, are only positive x's from 0 up to +infinity. Likewise, since the graph is exclusively in the first quadrant, the range is going to be, that's the y values, from 0 up to +infinity, okay? So guys, these are the 3 functions we're going to look at for the transformations. However, you can perform transformation on any function. Oh, let me write this down. Transformations can be performed, on any graph. I want to make that clear. because remember, I am going to be highlighting there's 3 of them, so that I don't want you to think, oh, that's it, just the 3 of them. No, no, no. You can do this with any function, guys, okay? So now let me go ahead and go back to the 4 different transformations we're going to look at. So I said number 1 was going to be the vertical shifting, which moves the graph up or down in the same direction, up or down, same direction. By the way, we can also say that this occurs outside the function. It's outside of the function, okay? And I'll show you the difference between outside and inside the function. So guys, here's what I'm talking about. I just showed you the absolute value graph. F of x is equal to the absolute value of x. And when we graph this, the graph looks like the letter V. Now, if I wanted to move this graph up, I might have an equation that looks like this. F of x is equal to the absolute value of x plus 3. So adding this positive 3 on the outside of the function, outside of the absolute value symbol, will actually shift the graph 3 units up. So it'll move the graph up 3 units. So what does this mean? Okay, so let's look, guys. Originally, when you graph an absolute value, the vertex, aka the tip of the graph right there, the vertex is usually at 0, 0. You know what? Let me drop this on the XY plane. There we go. Okay. So guys, if the vertex is at 0, 0 and we move it up 3 units, then the vertex is going to go up to this point right here. Okay. That's where your new vertex is located at. So rather than being at 0, 0, it's now at 0, 3. Every single point on the graph of this absolute value function will be shifted up 3 units, okay? Here's a quick example, guys. Let's say I had this point over here on the graph, okay? 2, 2. And then I took this same graph and I shifted it up 3 units. This coordinate point right here, 2, 2, on this graph is no longer going to be up at 2, 2, because I shifted it up 3 units. It's now going to be at 2, 5, because I went up 3 units. So I am adding 3 to the y components. And so guys, this number on the outside of the function moved the function up 3 units. So the number on the outside moves the function up or down. So let me go ahead and show you a different example, all right? So this time around, let me go ahead and do f of x, same absolute value function, okay? But this time around, it's going to move the function down, okay? So I have f of x is equal to the absolute value of x minus 2. Now, this minus 2 will move the function, shift the function down 2 units. So guys, if I go and sketch the graph of this one, rather than the vertex being at 0, 0, it's going to shift down 1, 2 units. This is where the new vertex will be at 0, -2. So which means every single point on the graph of this absolute value will be shifted down 2 units. So that 2, 2 right here, guys, on this graph, it is going to go down to, guess what? 2, 0. Because it's shifting it down 2 units. It was at 2, 2. You subtract the 2 from the y coordinate, it brings you down to 2, 0. And just like that, you're done. All right. So now, guys, here comes the second transformation. And the second one, guys, has to do with the horizontal translations or horizontal shifting, as in you're moving the graph left and right. Horizontal translation, horizontal shifting, same thing. This is where you're going to move the graph left or right. But guys, be careful with this one. In the opposite, let me underline this part, opposite direction. It's going to be in the opposite direction. So here's what I'm talking. By the way, guys, this one is going to happen inside the function. Inside the function. Now, what in the world am I talking about inside the function? Here's what I'm talking about, guys. Remember the quadratic function. Sometimes I refer to it as the square function because the power, guys, okay? A square function. When you graph the square function, this is what the graph looks like, guys. Okay, it's a quadratic, your vertex located at 0, 0. Now, if I want to affect the horizontal part of this graph, I'm going to make the changes inside the function, as in inside the square. So rather than adding 2 or subtracting 2 from x squared, it's going to be inside the function. So I'm going to do something like this, x plus 2 inside the parentheses. Did you guys hear that? Inside the parentheses. So if it was the absolute value, it would be inside the absolute value, okay? And then square it, okay? So guys, this positive 2 here, it's going to move the graph in the opposite direction. So rather than moving to the right 2 units, it's going to move to the left 2 units from the origin. So guys, let's look. When you go to graph this one, you're going to move left 2 units, 1, 2, plot your coordinate point, and then sketch the graph, guys. And by the way, it's the same shape. The only difference is you're translating the graph, you're shifting the graph 2 units to the left, 2 units to the left, right here. So then the vertex is no longer at 0, 0. It's now at -2, 0. I know some of you are probably saying, well, why is it a negative? Why is it not a positive? Because I'm seeing a +2 inside the parentheses. Here's why, guys. You're on the x-axis. Everything on the x-axis has a y component of 0. So if I were to take this -2 and plug it back in to the function, it has to give me a corresponding value of 0. So if I take -2, plug it back in here, -2 plus 2 is 0. 0 squared gives me 0. It has to make sense. So that is why we're doing the opposite. If we were to do a +2, 2 plus 2 would give me 4. As in 2, 4. That's not on the x-axis. That wouldn't make any sense. That's why you do the opposite. Okay, guys? So here comes another example. And for this one right here, guys, very similar problem. I'm still going to use the same function, but this time I am going to move it in the opposite direction. And it's still inside the function. This time it's going to be x minus 3 squared. Notice that -3 is inside the function. So therefore, it's going to move this graph in which direction? The opposite direction. So it's going to go to the right 3 units. So when we sketch the graph for this one, guys, listen, the vertex will no longer be at 0, 0, but rather you're going to move 3 units to the right, plot the coordinate of the vertex, okay? Same shape, you're still retaining the same shape because it's still a quadratic, and we're gonna do a rough sketch of this graph. So guys, this is what it ends up being. And of course, the vertex is gonna be at 3, 0. And that's the second transformation, guys. So now, I'm gonna go ahead and move on to the third one. And remember, I'm only going to 4 of them, guys. I'm not going to do all of them, okay? There's a fifth one.
The 3, 0 is supposed to look like a U, not a V, right?
Yes, a U.
Okay.
Absolutely, that's a U. Oh no, that's not a V, that's a U. Maybe I
Okay.
didn't put enough curvature to it, but yes.
Just making sure.
No, there's nothing wrong with that. All right, so guys, here comes the next transformation. And you'll like this one. This one is very straightforward. We're looking at the reflections. There's 2 types of reflections. Now, we have a reflection about or over the x-axis. Okay, that's what we're looking at. And there's another reflection about or over the y-axis. So the first one I am going to look at is the one about or over the x-axis, guys. So let's look, everybody. For the one over the x-axis, this is what this does to the functions. This one occurs outside of the function, outside of f of x. So guys, what it basically does is it flips the problem upside down, okay? It allows the problem to go in a different direction. So rather than opening up towards positive infinity because it's a positive function, it's going to be reflected over the x-axis, so it's going to open down towards negative infinity. So what in the world am I talking about? So let's look. f of x is equal to absolute value of x. If f of x is equal to the absolute value of x, guys, normally this would go up. But because we are now going to reflect this over the x-axis, the equation will now be, hold on a second, I wrote it in the wrong spot. Let's try this one more time. So guys, the reflection will be negative absolute value of x. See that negative on the outside? That negative on the outside is saying every single y coordinate. So you input a value, the output, every single output will be a negative. So when you graph it, the graph will open down towards negative infinity. Now guys, if you're not sure, test it out. If I plug in 1, what do I get back out? Negative 1. 1 comma negative 1 would be somewhere down here. If I plug in positive 2, what do I get back out? A negative 2. 2 comma negative 2 would be over here. If I plug in a negative 2, what do I get back out? A negative 2. And negative 2 comma negative 2 would be located right there, okay? So that's the reflection over the x-axis. Let me do it with a couple more, and then I will move on to the one about the y-axis, okay? Now guys, on the quadratic one, f of x equals to x squared. If I graph this one, because it's a positive x squared function, when I graph it, it's going to look like this. However, if I wanted to reflect it over the x-axis, this is what the function would look like. So when you graph it, the graph will no longer open up towards the positive side of the y-axis. It's going to open downwards towards the negative side of the y-axis. And again, why? If you're not sure, plug in some values, guys. If you plug in 1, you get a negative 1 right back. 1 comma negative 1 would be somewhere over here. Now, if you plug in 2, you get a negative 4. 2 comma negative 4 would be way down here. You see what I'm saying? So guys, this makes sense. And if you're not sure, go ahead, go to the T table, use a T chart, use a table of values, okay? This will verify what's happening. So that's the second function. Now here comes the third one. The third one is the square root function. Now remember with the square root function, guys, the original function is exclusively in the first quadrant. So if we want to reflect this over the x-axis, what is going to happen? We're going to have it on the outside of the function, that negative. To reflect this over the x-axis, every time we put in a value, we're going to end up with a corresponding negative y value, a negative value. So where do we go to find all these negative values? We go down to the fourth quadrant to find all those values, guys. Hold on a second. Oops. Wait a minute. Yeah. Hold on a second. I didn't mean that V right there. Okay, guys, let me use a different color here. Okay, there it is, guys. So this would be f of x equals to negative radical x. Again, guys, if you're not sure, do a table. Look at this. You plug in 1, what do you get back out? Negative 1. You plug in 4, what do you get back out? Negative 2. So 1 comma negative 1 would be right about here, and then 4 comma negative 2 maybe way over here or something like that, okay? That's a terribly drawn graph right there. So guys, that's the reflection over the x-axis. Now, this next one you need to be careful with. Here's why you need to be careful with it. When we talk about reflections, okay, when we talk about reflection about the y-axis, whoops, I'm writing the wrong thing, y-axis, okay? This one happens inside the function. So guys, this is why you need to be careful. Look, if I have f of x equals the absolute value of x, and I plug in a negative value in here for x, look at what's gonna happen. If I plug in that negative value for x, I am going to get the absolute value of negative x. When we take the absolute value of a negative, what do we always end up with? A positive. So essentially, whether I have negative x values, positive x values, I essentially end right back to the same function. So what I'm trying to tell you is this, guys. These graphs right here, the absolute value functions, we call them even functions, and they are symmetric with respect to the y-axis, and so therefore they are not, or you cannot reflect it about the y-axis, okay? So this transformation about the y-axis, okay, because these are even functions, they're symmetric with respect to the y-axis, there's no reflection, okay, because they're already even functions. What you see on the left is what you see on the right. So we can't do that for this one. The other function we can't do this for, guys, some of you probably have already figured it out, is of course the quadratic or the square function. And some of you may be wondering, why can't we do it on the square function? Well, let's analyze it. Just like with the absolute value function, if you have f of x equals to x squared, this is going to occur inside the function. So when you plug in that negative value into a quadratic function, guys, and you square it, what's going to happen? You're going to get the same thing right back, because when you square a negative, you also get a positive. So guys, look at that. We get the same function right back. So this one will not reflect about the y-axis. So therefore, the only one that's really going to reflect about the y-axis is pretty much the square root function. Now, when we talk about reflecting about the y-axis, I'm going to show you guys what it means, okay? If we have f of x equals to the square root of x, if we want to reflect this about the y-axis, and we know this transformation is going to occur inside the function will become f of x is equal to the square root of negative x. Oh, I can hear you guys right now. Some of you are saying, wait a minute, I thought we could not have a negative inside a square root. You are absolutely right. Well, what if we could find a way to ensure that we can cancel out the negative? What if we could plug in values that would make sure the negative cancels out? What values would we have to plug in here to get that negative to cancel out, guys? Think about it. If I want to eliminate a negative, what kind of values would I plug in to eliminate that negative? I have to do their opposite. So if I plug in a -1, then the negative would cancel out. So I would be left with a +1. If I plug in a -4, okay, this is what's happening, guys. Here, let me go to the side and show you, okay? If I plug in a -4, this is what it's going to become, a -4. A negative and a negative becomes a positive. So when I take the square root of 4, what do I end up with? +2. So guys, essentially, what am I doing? I am canceling out that negative. So the question is, where do you go? What part of the XY plane? Where? What quadrant in the XY plane do you go to find those negative X values that will cancel out the negative inside the radical, inside the square root, guys? So here's the bottom line. For this one right here, when you sketch the graph, okay, understand this, guys. We have to go to the negative side of the x-axis in order to find values that will cancel out this negative right here. So the graph will no longer be the graph in the first quadrant, but rather it's being reflected about the y-axis. So now it's going to end up in the second quadrant, because here all the x values are negative. However, the y values will be positive. So that -1, will be located right here. That -4, +2 will be located right about there. So guys, if you're not sure, what do? Go ahead, create a chart, go to the T-table, and use that to help you figure things out. So guys, that's the third transformation, and I'm going to go ahead and do one last one, and I feel like we're running out of time already. So I think I'm going to have to save the rest of this for next week, and then we'll go ahead and move on from there, okay? So guys, here's the last transformation, and that is the vertical stretching, and shrinking. By the way, there's a fifth transformation, which I am not going to go over, and I am going to save this for those of you moving on to pre-calculus. Now, this one right here occurs outside f of x. It occurs outside the function. And guys, what in the world am I talking about? the leading coefficient. This is what we're going to be looking at. So if you have a function such as f of x is equal to a times x squared, this leading value right here determines whether or not the function or the graph is going to stretch vertically or shrink vertically. Now, in order for it to stretch vertically, we look at the a value, and we're looking at the absolute value of it because sometimes the a value could be a negative. So you're just looking at the number value. So if that number, and I put the absolute value there so we can focus on the positive, just the number, is greater than 1, guys, then this graph is going to be stretching. What in the world does it mean to stretch? Think of a rubber band, guys. Think of a rubber band. When it stretches, it becomes a very thin graph. Yeah, okay? Think of a rubber band stretching. As in the graph will get closer and closer to the y-axis. However, guys, if your a value is between 1 and 0, the graph is going to shrink vertically. What does it mean to shrink vertically? Think of a hamburger patty. You are squishing that hamburger patty so you can make it as flat as possible, although some of you don't like them to be that flat, okay? So when you shrink a function, guys, it is getting closer and closer to the x-axis, so it becomes a very wide graph, all right? Now, as always, if you're not sure, what do? Plug in some values. So guys, let me show you what I'm talking about. I am going to reference the quadratic again. And this one is going to be a bit harder to show you guys on the tablet here, but just bear with me. It works, guys, okay? And I'll try and make it multicolors so you guys can see what I'm talking about. So let's say we have f of x equals to x squared, guys, okay? I'm just going to do a quick table, okay, so you guys can see this. If I go ahead and plug in 0, you know you get 0 right back. If I plug in 1, I get 1 right back. But if I plug in 2, I get 4 back. So if I graph this one, guys, the first function, I'm going to have a point at 0, 0. Okay, you know what? I need to plug in some more points in here. Let's plug in -1, -2. -1 will result in +1. -2 will result in +4. So when you sketch the graph of this one, guys, and I'm trying to be as precise as possible, this one is going to look like this, okay? There's your 0, 0, and then we have 1, 1, okay? And then 2, 4 is located right here. -1, 1 is right there. -2, 4 is located right here. So here's your basic quadratic function. All right, everybody. Oops. All right. So now, guys, I'm going to do it again, but this time I am going to change the leading coefficient, people. I am going to change that leading coefficient. And my leading coefficient this time is going to be 2x squared, okay? 2x squared, guys. So again, I'm going to go back to the table, and just to expedite this, I'm going to plug in 1, I'm going to plug in 2, -1, -2. If I plug in 1, I get 2 right back. If I plug in 2, I get 8. If I plug in -1, I get 2 right back. If I plug in a -2, I get 8. By the way, this is 8, this is not 6, okay? So guys, if I go in to sketch the graph of this, 1, 2 will be located right here. -1, 2 will be right there. And if I go to 8, I'm not even going to have enough room to go to 8, guys. 8 is going to be way up here when it's at 2. Hold on a second. Let me go ahead and undo that one right there. Okay. 2 will be located way over here. When it's at 2, guys, I'm far away. Shazam. I'm very, very far away. Now, here's what I want you guys to notice. Right here, once we plot this, guys, look at what the graph looks like. It's the same shape, but guys, notice it is closer to the x-axis. Okay, so now I'm going to do it one more time. Okay, so that second one was f of x equals to 2x squared. Okay, so I'm going to do it one more time, and here it is. This time I'm going to change that coefficient and I'm going to make it 1/2, guys. 1/2. I'm going to make it 1/2 this time. 1/2 of x squared. And I'm going to go to that table again, okay? If I plug in 1, what do I get out? 1/2. If I plug in 2, 2 squared is 4. What's half of 4? 2. Now, if I plug in a -1, I get positive 1/2. And if I plug in a -2, I get a positive 2. Now, let's go ahead and sketch the points. So 0, 0 is still right here. By the way, I missed it for that one. 0, 0 is still right here. When I plug in 1, I get a 1/2. Look at that, okay? And if I plug in a -1, I get a 1/2. Okay, now when I plug in 2, guys, I'm going to end up with 2. Where is it? Hold on a second. When I plug in 2, 2 squared is 4, half of 4 is 2. Yep. Okay, so I'm going to be right over here, and then right over here for this one right here. Now, guys, what I wanted you to see is this. The graph is flatlining on the third one. So as you can see, the third one with a coefficient of 1/2 is way closer. It's getting closer to the x-axis, as in it's becoming a wider graph. If it's becoming wider, that means that eventually that graph will flatline as the values of the leading coefficient are getting smaller and smaller, as in they're approaching 0. What's happening to that graph? That graph is getting closer and closer to 0 to the point where it will become a horizontal line. Because if the leading coefficient is 0, you will no longer have a quadratic function, but rather you will have a straight line, okay? So guys, I'm gonna stop right here with all these transformations. That was a lot to take in, but just know this. This is not going to appear on the test. This is in your assignments. It's not going to be on the test. So I'm gonna stop here and then I will take some questions from you guys, okay?